Oops, crap. Hello, everyone. Hello, everyone, and welcome to our PyData Global 2024 talk. I am happy to have on stage with me Nguyen, and he is going to be talking to us about improving LLMs alignment with complete and robust preference data. So without further ado, I will pass over to Sun, who will talk to you about this LLM topic. Thank you.
Right. Yeah, thank you very much for joining my session. So today I'll talk about improving LLMs alignment with complete and robust preference data. So my name is Nguyen, and I'm working directly with Professor Teja Tulabanova from UIC.
Sun, sorry, your screen is not shared yet. Sorry about that.
Oh, screen sharing. Can you see my screen right now?
Yeah, we can see the screen. Thanks.
Okay,
perfect.
So can you see the full screen?
We do not see the full screen, but we see a PowerPoint.
Yeah.
Slideshow.
So full PowerPoint. I mean, full. Yeah. All right. So I will start again. So hello everyone. So thank you for joining my session. So my name is Sun Nguyen, and I'm working with Professor Teja Tulabanhola, and also work for this project. I also work with Niranjan Uma and Aris. So we are trying to improve LLM alignment with complete and robust reference data. So some motivation. So large language model are redefining boundaries of machine intelligence, propelling us into an era where AI can assist us with complex everyday tasks. So as the capabilities surge, so the potential unsafe behaviors. So biases, inaccuracies, and harmful contents from the data the AI was trained on can lead to unintended consequences, right? So
sorry,
AI must do.
Sun, sorry to interrupt you, but right now it's not the full screen. It's not the presentation. It's the PowerPoint.
Really, I'm sorry. Yeah. Oh my gosh. Yeah. Sorry.
No worries. We should have.
Yeah, I will try to share the whole full screen for some.
Yeah.
Yes.
Perfect.
Can you see my screen?
I think this is perfect. Thank you.
Yes. All right. So should I start over?
Sure. By all means. Thank you.
All right. Yeah. So language model are redefining boundaries of machine intelligence. They can help us with complex everyday tasks. As the capability surge, so that the potential unsafe behaviors, the biases, inaccuracies, harmful contents from the training data can lead to unintended consequences. So therefore, AI must do more than just perform tasks, right? It has to understand and align with human values. So here's an example with Microsoft Pay chatbot in 2016, 2017. This is the chatbot that deploying in on Twitter, and within a day or two, user already taught this chatbot to provide unhelpful or very dangerous tweets or behaviors. Another example is from Google Bard from last year, where it provide untruthful answers that causes Google Alphabet $100 million drop in the stock market. Another example is the Google Gemini image generation incident, where the generated images are not a faithful representation of the actual real life characters, right? So as you can actually see this. Yeah, there's a lot of cases. So the below, the red ones are the failures case. And then we also have some successful with public facing AI, right? So for example, a famous ChatGPT from OpenAI, and later on there's Anthropic Cloud and Meta Llama, and as well as Google Gemini. So why is it difficult to manage this AI behavior? So the reason is writing the reward function for nuanced behaviors and hard to define action are very difficult, right? So complex tasks are not easily quantifiable. So uh, how can we teach AI models those concepts? So humans are not good at defining or performing complex tasks. However, they are good at recognizing them, right? So instead of evaluate so instead of writing the reward function like that, we can evaluate the complex tasks that the model are behaving. So and use that evaluations to guide AI models. For example, I have a robot. If we have a robot here uh, that doing a backflip, like the previous case, right? Can we just select, okay, left is perform better or right is perform better, and then use that as the reward signal uh, for the robot to explore in that direction. So yeah, so here also for LLMs, so here is the figure from the Instruct GPT paper from OpenAI that lay out the post training process that very applicable right now for all of the LLMs, right? So first they are doing supervised fine tuning to make sure that the model can follow the instructions. After that, they collect the comparison data and then train a reward model and use that reward model to as the signal for the reinforcement learning process. And here also like the direct reference optimization. So instead of reinforcement learning, we can direct fine tune LLM with the preference data, right? So this is called preference fine tuning. So in this talk, we focus on the collection of comparison data of reference data in order to train a reward model or fine tune it directly. So from the Instruct GPT paper, what they do to collect the data is they per prompt, they will have multiple answers, and then they ask a worker or a ranker to actually rank these responses. So as you can see that if we do this, it's very hard to do so because uh, the responses can be quite long and can be quite detailed, and it's very hard to like seeing everything and comparing everything together. Another way to do is to do pairwise comparison. So we have response 1 and response 2 right here. This is actually from ChatGPT, and then we are trying to choose which one is better, 1 or 2, right? So the way to do pairwise.
Sorry, quick
Yes.
interruption. Do you see you have the notification thing saying Airbnb sharing your screen? If you click hide, that's going to be a little bit better. Yeah.
Sure.
Brilliant.
Okay.
Thanks.
Yeah. Okay. Yes. The way to do this is, for example, I have a bunch of responses right here, and then I can do A versus B, A versus C, A versus D, and so on. And then after constructing the whole matrix like this, I'll be able to rank these responses, right? Or rank these tasks, right? This is actually an example from some person trying to prioritize their task, right? Yeah, so we can use this to actually rank the responses from AI from the models. to do preference fine-tuning. So the problem, but you can also see that you need to have a lot of comparisons, right? You need to do a lot of things. You need to do multiple comparison in order to get the ranking here. So the problem here is like collecting human preferences to fine-tuning these LLMs is a challenging process because it's prone to make mistakes. You got human prone to make mistakes. So this process also very vulnerable to incompleteness and adversarial corruption. It's time-consuming, labor-intensive, and require highly skilled participants, right? So doing this process, doing the reinforcement learning with human feedback or DPO training with this type of data can be quite unstable. So it's very difficult to scale this up to account for all human values. So what are the existing solutions for this, right? So one of the solutions is to design a new loss function or altering the loss function of DPO to account for the noisy reference preference, right? So there's some example is conservative DPO, IPO, or DPO. But these methods are indirect methods, right? So they only for reaction and mitigation. So it couldn't solve the actual problem with the data itself. Another one is just to replace human with AI, right? AI models or another LLMs. That yeah. But doing this, the LLMs that to rank these responses can also make similar mistakes because they are trained on human-generated data. And when human are the actual end users, do you actually want to remove the human from the loop, right? It's quite hard to do so. So why don't we attempt to solve the problem explicitly during the data collection process by controlling the quality of the data we receive? So there's some key cases to address here regarding the data quality issue, right? So the first case is the partially observed and uncorrupted setting, meaning that the data can be the data are missing, right? So for example, some comparison are missing because as the comparison as the number of responses increase, it's actually really hard to have all of the comparison, right? The comparison data. So it's presented by the question mark here. That's the missing data, right? And the second case is the labelers unintentionally or maliciously give the wrong preferences. So we call it the fully observed. Somehow all of the data got observed, but it's got corrupted. And the third case is when there's the combination of both, where there are missing data and also the data is not reliable, right? So there's some corrupted comparisons. So here I'm illustrated like there's some illustration. So it's just, so in the ideal case, we shouldn't have any unobserved and then corruption data, which is this one. But in reality, we observe this, right? So one of the solution we propose is called complete robust preference data for rearrest alignment of LLM. So in short, it's called Kurachan. So previously, what we do is we collect the data and then feed it directly to the RLHF or DPO process, and then get the final language model, which can be suboptimal. However, if we can attach this Kurachan module to the data collection process, so after collecting the data, we attach this to to process the data. Then hopefully we can get the clean reference data, and then with this clean reference data, we can train or fine tune a better language model. So how do we actually doing this, right? So for each prompt, actually there are multiple agents or multiple ranker that rankers that are ranking these responses. So ranker can be humans, AI models, or a combination of both, right? So each of the 0, 1 to K here can be any of them, right? And then each of them providing their own preference, right? References like this. But together, they will form a global noisy, global reference data, but they are also noisy and incomplete. However, fortunately, we can utilize the low rank characteristic of reference data under BTL conditions. So with BTL condition, the preference data will have the rank of 2 under the logit link transformation, right? So therefore, the first step we should do is in our normal space, space, we can transfer that to the logit link transformation using this formula to make the matrix low rank, right? And then we can use the low rank characteristic to actually solve our problems. So first of all, in the partially observed and uncorrupted setting, which the missing data case, we can use the matrix completion subroutine to complete the reference matrix. So in this case, we are using OpSpace. So this is also known as LRPR in Rekuma paper. So basically, we can use matrix completion to actually reconstruct this or get the values for the missing data, right? So this is actually very useful because we don't need to collect all of the comparisons, right? We just need to collect some of them and then use this method to actually complete the matrix, right? So to reduce all of the inconsistencies, so to reduce all of the mental exhaustion with the workers, right? For the fully observed and adversarially corrupted setting, so everything is observed, but then we expect that there's going to be corruptions, right? So in this case, we can use Rorachon, so which is a RPCA subroutine to filter out the corruption from the preference matrix. So we can use this RPCA can decompose the dense matrix and the sparse matrix. So the dense matrix is going to be the reconstructed data that is denoised, and then the adversarial corruption is going to be the sparse matrix. So how do we know that we should do this, right? So if we have this data, fully observed data, we can examine the singular values of this matrix. So if we can see that this matrix is high rank, then we know that there are potential corruptions, and then we can use the RPCA to actually get the reconstructed dense matrix here. And then with this sparse matrices of corruptions, we can, they are potential malicious intent answers or comparisons. We can prevent the user that provide these responses from continuing altering the results, right? So together, for example, if we have both cases where there are missing data as well as the corruption in the data, we can combine both Coratron and Rorachon together into Curatron, which is first we are doing matrix completion to get all the missing data, and then from that we're gonna decompose the matrix into the dense uncorrupted matrix and a sparse adversarial corruptions. So after that, we can use this dense matrix and then inverse that back to the original space. And then from that, we can bring the responses, something like this, right? And then we can use it directly for test time compute, right, as well, right? So we know that this red one, pink one is rank 1. So we can use that directly as the answer without any training. So it's a test time compute method. Or we can use this to form pairwise comparisons like this, and then use this for our LHF or DPO process to get the final language model that is pretty good. So basically, the solution is when we get the raw reference data per prompt, we're doing the logic link transformation. And then we're going to ask if there's any missing data. If yes, we do correction, which is matrix completion. And then after that, we can we ask, is the corruption expected? If yes, then we will perform rotron. And then after that, we inverse the matrix to the original space. Otherwise, if the answer of the missing data question is no, we can directly come to this question of if the corruption expected. If yes, we do rotron and then inversion. Otherwise, we just not doing anything. Right? So just straight to the original space. Right. So these are some experiments that we did. Right. So for example, this is per prompt, right? One prompt only. So this is the original matrix. So and then original ranking and then original singular values. So we see that this is actually low rank if everything is fully observed and is uncorrupted, right? So then we add some corruption into the matrix. We can see that the ranking is actually get altered quite badly, right? So this is the correct ranking. However, we got very bad ranking here, not correct, right? So and then the singular values is quite bad. So this is the high rank matrix. However, after our model, after applying our model or our method into this matrix, we get the reconstructed matrix that are highly correlated with the original matrix. And then we can see that the ranking is recover quite well. And we have the low rank matrix, right? And then we also propose a augmentation method where we have this original data. We add more data into the matrix that we know that they will receive like really low score. And then by doing that, we can further. It can work better with higher amount of corruptions. Right. So for example, I added more corruption in, and then if we just apply our method directly, we will receive this matrix, which may not be very correlated with the original matrix, but by using augmentation, we can get to a very good matrix here. Right. So here's the experiments where we try to see the connection. The combination of unobserved comparison and adversarial comparisons. Right. So we can see that the amount here is from 0 to 0.9, which is 90% for each of the axis. Right. And then we see that the more we have unobserved comparisons and the more we have adversarial corruptions, the worse the correlation between the corrupted matrix and the original matrix, right? So the red is bad and the blue are good, right? So we can see that between the corrupted matrix and original matrix is quite bad as the unobserved comparison and adversarial comparison increases. However, after applying our method, we can see that the comparison between the reconstructed matrix and the original is good, right? So we can see more blue here, right? Instead of this, we can see more blue here, right? With our augmentation method, it's even performing better. So it pushed the red away, right? So so this is quite good. For actual LLM experiment, we perform DPO fine tuning. So we're using the empty bench dataset single turn version that have 80 questions, and then each have 34 responses from different models, right? And then we inject dismissive responses into the 34 responses, right? In total, we have like about 39 responses or something. So with 5 dismissive responses. Then we corrupt the matrix to make the dismissive responses higher rank, right? So we're doing it by giving the dismissive responses higher scores and giving the actual higher rank responses lower scores, right? So do that. We actually make the dismissive response higher rank, right? So after that, to performing evaluation, right? We use alpaca eval. So it's very similar to empty bench, which is in instruction following benchmarking suit, right? And then alpaca eval actually calculate the win rates of the model of our model against a strong model like GPT-4. And then we can see that so if we perform DBO fine tuning on the original dataset, which is uncorrupted, we can see that the alpaca eval win rate is about 8.2% compared to GPT-4, right? However, if we do it against corrupted, do it with, perform fine tuning with the corrupted dataset, we get 0% win rate. After reconstruction using our method, we can get to 10.84%. So the goal here is not actually to compete with state-of-the-art model. So the goal here is to see that, okay, if we have corrupted data, how worse the model could be, right? This is quite bad, right? And we can see that the average length here is like significantly less than the original and recover versions, because this model only provide dismissive responses, right? So here's some example. So on the left side, the left side is the column of dismissive responses that we inject into the data set. For example, that's it's like no, that's not something I'm going to address right now. It's not relevant for me. So that kind of stuff. And then the right side is the column of corrupted model responses. So the model only, after the fine tuning, it's only answer, I don't have the patience for this, so I don't want to waste my time doing this, right? So this is the behavior with the corrupted model, right? So here's some takeaways. So it's very difficult to scale up preference learning to account for all human values. So the process is very vulnerable to incomplete and adversarial corrupted comparisons. So instead of indirectly solving the problem by redesigning the loss function from training process, we can solve the problem directly in the data collection process, right? So making it easier to collect feedback and make it the process more scalable. So our approach presented here can impute the incomplete comparisons, detect potential corruption, and identify the comparison that were corrupted by an adversary, and then recover the uncorrupted reference data with high level of certainty. So yeah, that's it. That's it for my presentation today. So thank you very much, and then I will be happy to answer any questions.
Brilliant. Thank you, Sun. I have showed a presentation question on the stage.
Yeah, let me try to, stop share and then try to get to the question. Yeah. So the question here is in your presentation, you indicated the partially observed data that is ultimately transformed. It is data matrix and embedding. So basically this data matrix is the scores, right? So from the pairwise comparison. So for example, uh, A versus B, as I would say, A is 80% better than B, and then A versus C is A is 30% worse than C. So those scores are the matrix.
Okay, brilliant. I think due to time constraints, that is more or less it. But I do want to note that the slides can potentially be uploaded into the resources tab. So everyone just double check the resources tab.
Sure.
And also, for anybody who wants to continue the discussion, head over to the PyData Global Discord, where like-minded individuals and Sun can also monitor the discussion there. And there will be a recording for the session that will be available shortly for so you watch it just in the same Your Meets link that you clicked on to join the current talk. So thank you again, and we will see you guys at future talks. Thank you.